So we are going to continue discussing our next chapter, which is titled Thermochemistry. This chapter is going to talk about energy and the changes that energy goes through. As you know, the energy that we get on our daily lives comes from the sun, but mainly they come from chemical reactions. The majority of the energy comes from the sun, but then there's reactions that take place that we are actually getting that energy from. For example, when we are doing combustion of gasoline, that's a chemical reaction. Production of electricity through coal. We also have when we heat our homes using natural gas, or when we use batteries for power. All of those are examples of chemical reactions that we use in order to produce energy. So our main focus in this chapter is going to explore energy and the changes that energy goes through. As you recall from the very beginning of our journey, we discussed what the definition of energy was. And the definition of energy is the ability to do work. And you guys were able to, I'm sure you guys recall that, the ability to do work. The study of the transformation of energy is called thermodynamics. In this portion of thermodynamics, we're going to be focusing on thermochemistry. So it's going to be a little bit more specifics, which is the study of chemical reactions and the energy changes that involve heat. The whole thermodynamics, that main concept, we will come back to it later on. But for right now, we're just going to be sticking with thermochemistry, which is that change that we're going to be looking at. Now, just like everything else that we have discussed, we are going to be looking at units of energy. Because, like you know, units are very important, and every topic, not every I would say every main I would say idea, I'm missing the word that I want, but anyways, units are very important. So we're going to discuss the units that we're going to be using in energy. The most common unit that we have is going to be joule, which is going to be a capital J. That's going to be our units, the ones that we're going to use the most. Joule is an SI unit. Notice that it's going to be, the definition equals 1 Newton per meter, or kilograms times meter squared divided by second square. So we can do 1 joule equals 1 kilogram times meter square per second square. Another unit that you have is the calorie, which is lowercase cal, and it's another commonly unit used in energy. A calorie is defined as the amount of energy needed to raise the temperature of exactly 1 gram of water by 1 degree Celsius, which 1 calorie, so 1 little calorie equals 4.184 joules. Now, if we're looking in the field of nutrition, we're going to have the big C, big calorie. And that's just to distinguish between the other calories. So when we're talking about big calories, we're talking about nutrition calories. And those are gonna be 1,000 little calories equals 1 big calorie. So this relationship here. that relationships here. So this unit is very important that you become familiar with them because we are going to be using them constantly. And so make sure that we go, you know how to go from one unit to the other um, to be able to convert. In this chapter, we are going to be discussing the first law of thermodynamics. Um, the first law of thermodynamics pretty much says that energy can be observed from one form to the other, but it cannot neither be created nor destroyed. So we have the ability to convert energy. We have, for example, and I've seen it, you've seen it a lot, how we have the ability to convert it from kinetic energy to potential energy or potential energy to kinetic energy. Um, so you've seen that, for example, if you're sitting down, um, you know, you have potential energy. The minute you stand up and you start doing work, you have converted that energy into uh, kinetic energy. So want to make sure that you remember though the first law of thermodynamics. It kind of it's similar to what we discussed is the for the law of matter. So make sure so it's not going to be as difficult to remember because we actually have already encountered it. Some definitions for different forms of energy. We have electrical energy, and within electrical energy, we have kinetic energy, which is the energy associated with the flow of electrical charge. For example, protons and electrons. Heat or thermal energy. In there, we have kinetic energy, which is associated with the molecular motion. We also have light or radiant energy, which an example of that will be kinetic energy. Nuclear, which we have potential energy, which is associated with the energy in the nucleus. Then we have chemical energy, which is potential energy due to the structure of the atoms, the attachment of the atom's position relative to the molecule. So these are just different forms of energy that it will be very helpful for you to become familiar with it. Okay, so moving on, we are going to give you more definitions, and these definitions are going to be the way we're going to be transferring energy from one form to another. So it is important for us to be able to determine or to define where the energy is coming from and where is it going to. One convenient way to kind of define this is to, for example, realize what the system is and what the surrounding is. For example, if you have a beaker with water to a container with their like chemical reactants and products, so the water will be like the reaction itself, that will be considered the system. If let's say you're making a soup, everything inside the pot or the ingredients are considered your system. Everything else in the universe is considered the surroundings. Remember that the universe is going to be the system plus the surrounding. The system is typically the part of the universe. So the system is what's being studied. We have the flexibility of, as a scientist, we are able to define the boundaries of the system. Like for example, we only want the stuff inside the pot, or do we want the pot to also be part of the system? So you have to be careful how to define this to make sure you know whether energy is coming into the system or going out of the system. So notice here we have that the system are going to be your oxygens and your hydrogens. That's what's being studied. Everything else, such as the cylinder, the piston, and everything beyond that is considered the surroundings. Now we have three types of systems that we want to go over. We have three types of systems that we want to go over. And first, we have the open system. In an open system is in which matter and energy can be exchanged with the surroundings. Matter and energy can be exchanged with the surrounding. That's an open system. And then we have, this will be an example for this will be a uncovered pot of boiling water on the stove. That will be considered an open system. Heat comes into the system from the stove and water releases steam, right? So it's releasing heat. We also have a closed system. System that can exchange energy but not matter. So this is an example. So a closed system, you are able to exchange energy, but you are not able to exchange matter with the surroundings. This is the one that we use most commonly in our experiments. Because you are able to kind of manipulate the mass, right? Then the last but not least, so the reason why, so remember, we don't, for the closed system, we don't lose or gain mass, which means because matter is not involved. But however, we are going to exchange energy, and keep in mind that energy can be exchanged through work or through heat. Then we have an isolated system, which is the third system, in which neither energy nor matter is exchanged with the surrounding. It's an isolated system. We are not exchanging, heat or mass. So it's just isolated. The best example that I can probably give you is going to be when you go to work and you have the thermal where you have the coffee. You're technically maintaining it, so you're not gaining any water, right? So it's just staying there. You're not exchanging any heat. However, that is not a perfect example, because eventually the coffee is going to get cold. It does like, keep it warm for a long time, but it's not a perfect isolated system. So that's the best example that I can give from an isolated system. Now, moving on with our discussion, we are going to keep continuing talking about other terms, and now we're going to be discussing internal energy. Internal energy, which is going to be capital E. Okay, sorry, give me 1 second. So internal energy, which is represented with this capital E, is going to be defined as the sum. So internal energy is going to be the sum of kinetic energy and potential energy of the particles within the system. So whatever, and like if you have a reaction, you want to know the kinetic energy plus the potential energy, and that will be equals to your internal energy. Some books will represent internal energy with the letter U. They mean the same thing. I believe they do this a lot in physics. Keep in mind that kinetic energy includes not only motions of the molecules inside the system, but the motions of the atoms and subatomic particles within the atoms. So internal energy is going to describe all the energy. Internal energy is a state of function. What does that mean? What a state of function means is that it doesn't matter how you arrive to your final answer. It doesn't matter which path you took. What matters is that you got there. So the basically the value of a state of function only depends on the present state of the system, not the path that the system took to reach to the end game. A good example that I can give you is, let me think. If you're going, I think I have an example coming up later on. Um, let's see. Um, So a statal system will be kind of like height. So we're gonna discuss that it's coming up, but let's say you had to go up a mountain, and you have to go 5,000 feet up. It doesn't matter which path you took there. It just matters the distance that you went, that it took you to get up there. And like I said, I'll mention it in a minute. And that's what we represent the state of function. It's going to be shown in that little triangle, pretty much saying that it doesn't matter the path that you took to get there. It just matters the initial state and the final state. That's what they're pretty much discussing. Okay, so now we're going to discuss the sign of energy. Each energy is going to have three parts, each quantity in thermodynamics. So right now we're just looking at energy, but we also have heat, we have work. But each quantity in thermodynamics is going to have three parts. It's going to have a number, a unit, and it's going to have a sign. And the sign is what we need to understand. So think of it when we are discussing energy. If you're gonna define your system. If the system is releasing energy to the surroundings, that we're saying that the delta E of the system is negative because it's losing, but the surrounding is going to be positive. Think of this as your bank account. When you do withdrawals, your bank, let's say your bank account is your system. When you're withdrawing from your bank account, you have a negative side. And the surrounding, which is whoever you gave the money to, is happy. They get a positive sign. So this is when energy flows into the surroundings. So notice that the energy is flowing from the system to the surrounding. So the system is negative, as you see it here, and the surrounding gets a positive sign. On the other hand, so here's an example. If we look at a reaction itself, here you have a reaction where, let me write it here. Here it goes, I'm circling right here. In this case, your reactants have more energy than your products. The reactants have more energy than your products. In this case, there will be a net release of energy into the surroundings because your reactants have more energy than your products. So there will be a release of energy. So the overall reaction, the overall process is going to be a negative sign. However, if we switch that and we turn it around where the reaction, products, here's your products, have more energy than your reactants. What's going to happen is that the reaction, in order to proceed, is going to need energy from your surroundings. So in this case, the reaction, it's going to be a positive because it's getting energy from your surroundings, and your surroundings is going to have a negative sign. So these are called these are going to be your energy diagrams, in which we kind of show the final conditions of your reactants and your products. So notice here, if the system itself, for example, is if you're, let's look at a piece of ice, a piece of ice being the system. If you want the piece of ice to melt, the ice is going to get energy from the surroundings. So it's going to be a positive E. However, if we're dissolving, or we're trying to get water into, yeah, if we're dissolving the ice, it's going to be the opposite. We're going to have to, if we're trying to freeze, or if you're trying to freeze the water, we're going to have to input energy. So it's going to be the opposite process. Going back to the whole state of function, as I was mentioning, what that means is, let's say you have to go up a mountain. In this mountain, you have to climb 10,000 feet. Now, there's two paths that you can take. You can take path A, which is going to make you go up 12 miles, or you can take path B, which you have to go only 5 miles. What state of function means is that it's going to be final minus initial. So it's going to be 10,000 minus 0. So overall, no matter which path you took, the distance that you climb was the same. So you can either take the long way or the short way. It doesn't matter how you arrive there. It matters the distance that you went through, that you went up. So as I mentioned, thermodynamics is any quantity. So far, we only have discussed energy, but any quantity is going to have three numbers. Three parts. You're going to have a number, a unit, and you're going to have a sign. Now, the positive E is going to result when the system gains energy from the surrounding. A negative E, so a negative E is going to be when your E initial, it's greater than your E final. That's when the system loses energy to its surrounding. So E initial, and then for this one will be when E final has more energy than your E initial. So those are going to be these two, the number and the unit is going to tell you the magnitude of the change. Magnitude of the change. The third part, the sign, is going to tell you the direction. It's going to tell you that direction. Okay, moving on. So as I mentioned, we have the ability of exchanging energy with its surroundings. So the system has the ability to change energy with its surrounding. This can happen in two ways. It can be exchanged as heat or as work. As you can see, heat, we are going to represent it. I don't know why this is not doing that. Heat, we're going to represent it with the small letter Q, and work is going to be represented with the letter W. So I just want to remind you that um, like try to think of energy as your bank account. Every time you have a deposit, it's an increase of energy of the system. That's going to be a positive E. So if you're depositing into your account, that'll be a positive E. Where a withdrawal decreases the energy of the system. So you're gonna have a negative E. So that should be able to help you. So you wanna remember that delta E is going to be Q plus W. When heat is added to a system or work is done on a system, the internal energy increases. That's a very important point. So let me write it down. When heat is added to a system or work is done on a system, its internal energy increases. So therefore, when the heat is transferred to the system from the surrounding, Q is going to be a positive value. Q is going to be a positive value. And we're gonna get into that a little bit more. So Q is a transfer of thermal energy between substances. Notice here we have two substances, one is hot and one is cold. They are separated. When they come in contact, heat is always gonna flow from the hottest, from the warmer substance to the cooler substance until equilibrium is reached. So just to recap, and then we're gonna use other terms to kind of add to this. We're going to use the word exothermic and endothermic. An exothermic process is a process in which heat is lost, such as combustion of gasoline is an exothermic process. Endothermic process is going to be things like melting in ice, is in which the system is absorbing energy. The way we're gonna represent it, exothermic, we're gonna represent it with a negative Q. Endothermic, we're going to represent it with a positive Q. To summarize this whole process of exchanging energy, we're going to have this chart, which is going to help you identify when Q is going to be positive. So when Q is positive, that means that the system gains heat. When Q is negative, that means that the system is losing heat. When W is positive, that means the work is done on the system. When W is negative, that means the work is done by the system. When is delta E positive, is gonna, it means that the net gain of the energy by the system is gonna be negative when there is a net loss of energy by the system. Okay, so now that you know that, let's do some practice problems. For example, here you need to figure it out. What's first, identify what's the system and identify what's the surroundings, and decide whether you're going to have Q or W, whether you're going to have Q or W. So I pause it. Okay, so the answers to these problems were, the first one we were talking about Q, And the answer is plus W plus Q negative. Now we have another problem. Take a minute to read it. It says calculate the change of internal energy. So remember the internal energy is going to be Q plus W. Okay. And then it's telling you that a system of, so this is Q and work W. Now you want to remember that Q is going to be positive when we have endo. Q is going to be negative when we have exo. And then W is going to be positive when it's on the system. And W is going to be negative when it's done by the system. So here, we know that Q is 300, but is it positive or negative? Energy is absorbed right there. It's telling you that it's positive. Okay. Now, what is W? W is going to be 400. But is done on the system. So that means that it's positive. So the answer to this problem will be 300 plus 400, 700 joules. And that'll be your answer to the problem. So the key is to identify the sign. That's what's going to make sure that you understand. It's going to be the sign to make sure you get it right. Okay, so I have another problem here. Take a minute to read it. So we make this system, and this is the surrounding. The system releases, so it's releasing 700 joules of energy. So that means that since this is the system is releasing, so that's going to be a negative. So delta E is going, and then that means that this is gaining 700, right? Because if the system loses, the surrounding must gain it, and then it's work done. So this is going to be 300 done by the system. So the system is the one doing it. So it's going to lose 300. Okay, so basically the way you're going to do this is 700 joules plus 300 joules. That's going to be 1000, right? That's for the surroundings because this is gain for the surroundings. So delta E is going to be, sorry, this is for the surroundings, but delta E, the surrounding is going to be negative 7. That's negative 300 joules. Because we're looking at it with a point of view of the system, not the surrounding. So in this case, you're going to have negative 1000 joules. So this is if I was to ask you with respect to the system, but I mean to the surroundings, but I'm not asking you to the surroundings. I'm asking you with respect to the system. And that's important because a lot of, for physics, they tend to do it with point of the surroundings. We do it with point of the system. Anyways, I think this will be a good stopping point for this part before we get into a little bit more complicating problems. Hello, we are going to continue with our discussion and we are going to move on to figuring out how to measure internal energy using calorimetry, which is an instrument on constant volume So our volume won't be changing. Recall that your internal energy is heat plus work. We can determine the internal energy if we measure the heat and the work of a reaction. The easiest way of doing this is if we assume that W is going to be 0. We're saying that there is no work being done. So when that's the case, we are going to have delta E equals the heat if W is 0. And the reason why we can make that assumption, was not an assumption, well, we can make that statement. Let me go back. So the reason why we can make that statement is because when our W, we are going to assume that we're not doing any work on it. In practice, it is not possible to actually see the temperature changes on individual reaction. Instead, we look at the surrounding, because within the, since it's in a closed system, you're not, if you open it, you're going to be obviously escaping heat. So what we do is we measure that surroundings instead. The surroundings, we can control it. So we say Q system equals negative Q surrounding. Remember, whatever one gains, the other one must lose in equal quantities. Now, in this case, the surroundings is called a bomb calorimeter, and that's an instrument that is sealed and is insulated and is filled with water. Um, this is how pretty much it looks. And what we see is that we are only going to be concerned with heat being transferred from the surroundings to the system, or system to the surroundings. Notice that when we use a calorimeter, we're going to need a constant, and the constant has these units. We're not going to be touching much on a bomb calorimeter, but you're going, it's good to become familiar with it, because that's what they use. So most reactions are going to be performed in an open system. Um, like when you have a beaker in the bench, in your bench, and in this case, you're gonna realize the work and heat are being exchanged between the system and the surrounding. However, the work exchange is often real small, and or that is so small that we pretty much ignore it. So that's why we put W equals 0. Um, the heat that is going to flow is the one that we're going to pretty much account for. Now, we're going to be discussing enthalpy, and enthalpy is going to have represented with this capital H. It's the state of function, which means delta H. It's a state of function that relates the internal energy, pressure, and volume. So it's relating internal energy, pressure, and volume. At constant pressure, the change of enthalpy equals the internal energy plus the pressure and change of volume. So this is at constant pressure. At constant pressure, this is how we can calculate enthalpy. Now, we can simplify this equation by knowing that pretty much, notice enthalpy is I told this is a state of function. The way we can simplify this equation is by realizing a couple of things. Delta E, and you don't need to know this. I mean, you don't need to solve for it, but delta E from the previous slides, we know that is Q plus W. Well, in this case, W equals negative P delta V. So if you think about it, you were substituting this with negative P delta V. So what we come out of from this equation is that delta H equals Q. So the enthalpy is simply equals the flow of heat at a constant pressure. So this is at a constant pressure. to calculate enthalpy, we're just gonna figure it out Q, because delta H is going to be Q. So enthalpy in general will be the change in heat of the system at constant pressure. Now, there are some terms that we have to go over in the same matter that as Q, delta H is positive when heat is transferred from the surrounding to the system. Reactions that absorb heat from the surrounding are known as endothermic process. On the other hand, delta H will be negative when heat is transferred from the system to the surrounding. We call this an exothermic reaction. So you want to make sure you become familiar with both. So remember, for endothermic, we're going to have a positive delta H and also a positive delta Q. For exothermic, we have a negative delta H and we have a negative, a negative delta H and a negative Q. Okay. All right, let's move on. And we are going to be calculating the change of enthalpy. So remember that I told you that change, that since this is state of function, what that means is supposed to be a negative here and an equal sign here. What that means is that we don't care how the path that the reaction took. We just care about the overall answer because it's a state of function. So what that means is we will take the enthalpy of the products. So in this case, the products minus the enthalpy of the reactants. And that's how we can calculate the enthalpy of the overall reaction. This quantity delta H is also called the enthalpy of reaction or heat of reaction. So notice what we do is in order, if I wanted to know delta H of this reaction, I will figure it out the delta H of my reactants and my products. And then you just do products minus reactants. And depending if that number is positive or negative, you can determine if the reaction is exothermic or if it's endothermic. Enthalpy is an extensive property. So we went over that in chapter 1. Enthalpy change for a reaction is equals the magnitude, but the opposite in sign to delta H for the reverse reaction. So for example, if forward is 100 kilojoules, backwards will be negative 100 kilojoules. The enthalpy change of the reaction depends on the state of the reactants and the products. So it's gonna matter where there is a whether we're discussing solids, liquids, and all of that. Here we have an equation. And they are giving you the enthalpy of the whole reaction. So what they're saying is, if you have 2 moles of aluminum plus iron 3 oxide and yields iron and aluminum oxide, you're gonna release 50 kilojoules of energy. That word negative here is saying that it's an exothermic reaction. That is an exothermic reaction. We are going to use this equation and use stoichiometry to make relationships that are going to help us. For example, notice here, this equation, if I wanted to make a relationship between this reactant, what it says that for every reactant with this that I react, assuming you have everything else, you're going to generate that much heat. So because it's a balanced equation and this is given to you, it's considered that you can use it as a conversion factor. And notice you can also make a relationship between your moles and the heat is released of oxygen. But you can also do it with the product. So you can make it very convenient um, to get to your desired answer. So let me explain how your exam question will be. How much heat is involved in a complete combustion of 13.2 kilojoules of this compound? So the first thing that you're gonna have to realize is that you will be giving how much energy in generally you're going to be proceeding. So uh, let me write the equation here so you can see what I'm talking about. So in this case, C3H8 gas plus 5 oxygens yields 3 carbon dioxide plus 4 waters, and this is going to be delta H negative 2044 kJ. Okay. Now, notice what they're saying here. What they're saying is that this is the complete combustion, but what they're saying is that instead of starting with 1 mole, you're starting with this many, 13.2 kilograms. So that's what you're starting instead of, because here, for every 1 mole that you generate, you're going to have negative 2044, right? So we're gonna need this. But they're telling you, well, what if you start with 13.2? How much heat are you going to generate? So the first thing you need to do is go from kilograms to grams, from grams to moles, and from moles, you're going to go to kilojoules. So how are we going to do that? Well, you know how to go from from kilograms to grams because you know that 1 kilogram equals 1,000 grams. So now you got rid of your kilograms, but you still have 1,000. Now at the top, you still have grams left of C3H8. So what you're gonna do is you wanna get rid of those grams, and this is your molar mass of C3H8. Now you cancel your grams of C3, but at the top, you still have moles of C3H8. And the way you're gonna cancel that, this comes from the equation. Because for every mole of this reactant, you're going to release that much energy. Now, all you do is cancel and do your math, and you should develop your final answer. Okay, here's another question for you to try it on your own. So the first thing you're gonna have to do is you're going to write the equation. How much heat is involved in diamond? So remember that diamond is gonna be carbon, and it says combustion. So you're dealing with a combustion reaction. What that means is that you're going to react it with oxygen. And then for combustion reactions, you're always going to have carbon dioxide and water. And you're going to make sure that it's balanced. Diamond. We don't need to, why is it not working? Well, you're just going to, this one, you're not going to generate water. You're just gonna have your carbon dioxide, sorry, combustion reactor with water. So it's balanced and it's telling you that heat is going to be negative 395.4 kilojoules per mole carbon. Now, the question is asking what happens, what will your answer be if you, instead of starting with 1 mole, you're starting with 0.483 grams of your diamond, which is your carbon. So what you need to do is go from 4.83 grams of carbons goes to moles, and moles, um, so here you're gonna use molar mass, and in here you're gonna use the balance equation. And then here you're gonna end up with kilojoules. So pause it and try to do it by yourself. Here's the answer. Here's another question that I will like you for you to try it on your own. Here's the answer. Another question for you to try it on your own. Here's another question. The answer. Question. And here's the answer. Okay, so now we're gonna start going over calorimetry. And what calorimetry is the study of heat transfers by measuring the temperature change. For example, if this is what the calorimeter looks, if inside you put metals, like pieces of heat of metals that are heat hot, that heat that is going to be that heat is going to be transferred from the metal to the water. That the heat that the water gain is going to be the same heat, the same amount of heat that the metal lost, because we're not going to be losing any. Um, and we're going to go over some examples. This is the calorimeter, which is the is going to be what we're going to be using. Now we're going to be using every substance is going to have specific a heat capacity. Heat capacity is going to be the amount of energy required to raise the temperature of a substance by 1 Kelvin or 1 degrees Celsius. If the amount of substance heated is 1 gram, it is the specific heat. So be careful with those two terms. Notice here we have the specific heat of substances. So that's the most common, that's what we use the most to just kind of make it, to just make it a little bit more interesting and be, sorry, more specific. We're gonna, and so to do the same units, we're gonna be actually just using specific heat most commonly. Um, For some reason, it's not showing you guys correctly the equation, but here will be Q of solution equals, so that's gonna be your heat capacity. M stands for mass of your solution. T stands for your change of temperature, equals Q of negative reaction. So remember, if the solution is losing, the reaction is gaining. So they have to be opposite. So here we have an example of a type of problem that you can be asked. For some reason, it's not showing. The question says, how much heat is absorbed by a copper penny with mass that is 3.10 grams and temperature rises from 8 Celsius to 37 degrees Celsius. So the equation that you're going to be using is this. Q equals M, I call it MCAT. Now, the they already giving you the grams. The grams is 3.10 grams. Now, the specific heat, it's given, this will be given to you also. It's also in your textbook, but that number will be given. The change of temperature is going to be final minus initial. So the final is 37 minus negative A. It will be 45 degrees Celsius. When you put everything, notice that your grams cancel, your Celsius cancel, and the only thing that's not cancel is going to be your joules, which makes sense because they're asking you for heat. Every time it's asking you for heat, your units are going to be joules. Also notice that your answer does make sense because it says how much heat is absorbed. So we know that your final answer should be positive, not negative. Here's another question that you might want to try on your own. So notice that they're giving you your C of water. They are giving you your mass, which is 7.40 grams. And then you need to calculate change of temperature, which is final minus initial. And the equation is going to be Q equals M cat. And here's your answer. You can also be asked this question a little bit different. Notice in here, they're saying you have 75 grams of water at 10 degrees Celsius. You add 38.50 joules of energy. What will be the final temperature? So you want to go back to the equation M equals, Q equals M S change of T. Now, you want to recall that I will always give you the C unless I'm asking you to calculate it, but in this case, the C is going to be 4.18 joules grams per Celsius. So they're giving you your Q because this is the unit of Q. So you have 38.50, and then they're giving you M, which is 75.0 grams. I gave you CS because it's 4.18 joules per grams over Celsius. And let's solve for change of T. So that makes it easier. Change of T, it's going to be 38.50 joules, 75.0 grams times 4.184 joules grams or Celsius, and that should give me 12.28 Celsius. But keep in mind that they want to know the final temperature. So this change of T equals T final minus T initial. Well, we have the change of T, which is 28.28, and we have T initial, which is 10.0 Celsius. So when you do your magic from there, you should be able to figure it out that your T final is going to be 22.2 Celsius. And that should be your answer. So try to do this problem by yourself. There's another problem where in this case it's asking for the specific heat. So that means that you are giving, so Q equals M. Your Q in this case is 849 joules. Your mass is 95.4 grams. You're looking for CS and the change of temperature, it's gonna be final, which is 48.0 minus initial. And basically you're gonna solve for that. When you finish, your answer should be 0.387 joules gram per Celsius. There's another question. It says how many joules, so that seems like you're looking for Q. Your final answer should be negative 6120 joules. This is an exothermic reaction. Now, so far we have only been discussing one object, but what about when you have two objects, like you place the metal, like you're gonna see in lab, inside of the water. So we need to calculate the amount lost. So the equation you're gonna be using is this, to make it more formal is Q equals 0, right? Because you're not gonna gain or lose. And it's gonna be on one side, you're gonna have M of water, or the, the specific heat of water, and the change of temperature of water. On the other side, this is plus your mass of your metal times your C of your metal and the change of T of your metal. And this is how we're gonna calculate how much heat was released or how much heat was transferred. So notice here, we have this question where they're asking for the final temperature. They're asking for the final temperature. So this, it's a little bit more, it says a piece of metal at 85 degrees is added to a water of 25. So think about it. The metal is hotter than the water. The final temperature of both, the final temperature will always be the same for the metal and the water. So based on that, which of the following statements is true? Your answer should be 4. Now I have another question here where it's saying a cube of aluminum initially at 45 degrees Celsius is submerged into a 103 grams of water at 15.4 Celsius. What is the final temperature of both substances at thermal equilibrium? So what they're looking is for T final. So the way you want to do this problem is you want to set it up in a way where you have them equals to each other. So you have information about a metal here and you have information about the water. So let me see if I can do it here, if I have enough space. Okay, I think I should be able to. So first we want to recall the equation, right? So the equation is going to be Q equals MCS. excuse me, change of T. Now, for this one, we are going to see, I'm going to know this. It says that the cube of aluminum is 45 degree, 45.8, and your water submerged into a water of 100 degrees of 15.4. So it looks like that metal is losing heat. Sorry, ignore this. This is wrong. So because this is hotter, it seems like the metal is going to be loose. And actually, it doesn't really matter which method you use, you still come out with the same answer. So in this case, what you're going to do is you're gonna set these two equations equals to each other. So you're gonna have m. I'm gonna make this whole sign negative. M of your metal times Cs of your metal times your change of temperature of your metal, and this is equals M of your water, Cs of your water, and the change of temperature of your water. Now, let's start filling out what they're giving us. What is the mass of the metal? The mass of the metal is going to be 32, 32.5 grams. And then the CS is going to be, that number is going to be point, it's not here, but it should be given it to you in your book. It's gonna be 0.903. And you have T final, which is what you're looking, minus your T initial. It's going to be 45.8, and then equals your water, which is going to be 105.3 grams. The change of the specific heat is 4.18, and times T final, which is what we're looking for, and T initial is going to be 15.4. Okay, so pretty much what you're now going to do is you're just going to solve for your you're just gonna solve for your T final. So from here, this side, when you do this side, you should get negative 29.3475. And from here, you should get 440. Sorry, not this. I'm doing this whole thing. Kind of not shortcuts. Okay. So this answer here should be negative 29.3475. I'm gonna just bring this down. The final minus 45.8 Celsius equals, this answer should be 440.154 times T final minus 15.4 Celsius. So don't forget, for here, you're gonna have to distribute. So when you do that, you should have negative 29.3475 TF plus, because a negative turns a negative, it's going to be 1344.115 equals 440.154 TF minus 6778.3716, and then collect like terms from there, and you should generate your final answer. Your T final which is going to be the same for both. Let me do it in a calculator. It should be 17.3 Celsius. That's your T final. And you're going to have one of these on the exam. There's another question here that you can try yourself. And in this case, you're looking for specific heat. So you're gonna set them up equally. Try it by yourself. And here's the answer for this question. We definitely can do some problems on these ones if you guys want, just because this is gonna be heavy on the exam. There's more practice in the lab, so make sure that you work with your lab instructor and ask him to give you more of these practice problems, because I can do the stuff that is not covered in lab, but this is definitely covered in lab. Here's one more question where you guys can try it. And once again, this one is asking for T initial. So you're looking for T initial of your gold, and your answer should be 732 degrees Celsius. Okay, so I'm gonna stop here. We have one more topic to cover, and then that will be it for this chapter. Okay, let's wrap this chapter up. So one way of calculating the values of enthalpy delta H for a reaction, it involves manipulating reactions of that we know the values of delta H. Um, when chemical reactions are added, so if you add a chemical reaction, like 3 chemical reactions, you're going to have a different overall chemical equation. To figure it out, so I'm gonna give you an example. So let's say that you have square plus that gives you a circle plus a star, and then this will give you a that plus I don't know any more figures. Let's do that squiggly line. And then you have 0 plus x. So let's say you knew the delta H of this. Let's say it's 100 and this one is 200 kilojoules. Those are reactions with known delta H value. If we sum these reactions, cancel that. Don't cancel that because you have 2 triangles. So it's going to be 2 triangles plus a square, plus an infinity sign, 2o plus 2x. Now we don't know the value of this new reaction. This is not known. However, we can use this. If you add this, since we added this to reaction, we can add those 2 delta H's to give us the delta H of our desired so this of the desired reaction. So this will be like 300J. So this method is called, this principle is called Hess's law, where we pretty much manipulate equations to get us to our desired overall equation. So Hess's law pretty much says if a reaction is carried out in a series of steps, like small reactions, delta H for the overall reaction equals the sum of the enthalpy changes of the individual steps. Because delta H is a state of function, we pretty much don't care the steps that we took to get there, as long as like we get there. We just care about the big numbers. So you're gonna have to manipulate those reactions, and we are gonna have an example. Oops. So another, another topic I want to mention, and we're gonna have some practice. Hold on a second. I might want to do. Let's stop this. Let's get an example of Hess's law. Notice here we have an equation. This is the multi-steps. This equation is known and it has a known value. We have a known enthalpy, and we have the same for the second reactions. However, we don't have the enthalpy of the methane plus oxygen that gives carbon dioxide and water. The way we're gonna get that is by adding the enthalpy of reaction 1 plus the enthalpy of reaction 2. If we do that, we get the enthalpy of our desired equation. Notice that when we manipulate the reaction, you want to make sure when a reaction is multiplied. So if you take your whole reaction, for example, this is the reaction, but notice that what we want is to have 2 carbons, not 1. So what we're going to do is take this whole reaction and multiply it by 2. If we do that, that means that we also have to take a delta H and multiply it by 2. Whatever we do to the reaction, we must also do it to the your delta H. Another thing is, let's say, or another scenario is, this is the equation that is given to you. This is the equation that is given to you. However, you want the equation below. What you realize is that basically your reactants and your products are flipped. So if you flip the reaction, you're going to have to change the sign of your enthalpy. So by flipping the reaction, you are changing the sign of your enthalpy. So once again, whatever you do to the reaction, you must do to your whatever you do to the reaction, you're gonna have to do it to your enthalpy too. Here's another question, another example. This is what you need, and this is gonna be almost exactly what you have on the exam. You are given this reaction and you are asked to find your delta H. What is the delta H? We don't know it. However, they're going to give you a series of steps. So notice that you have given 3 steps here. And somehow, when you add these steps, you're going to have to, you need to end up with an equation that looks like this. There are multiple ways of doing it. There's no right or wrong as long as you keep track. And this question is on the exam and students always get it wrong. Let's start by looking at NO. You want it on your product. Where is it? Where is it in your series of steps that they're giving you? You're going to see that that one is going to be in step number 2, right? And notice that we want 4, oh sorry, in step number 1, but we only have 2. So what am I gonna do to this reaction? I'm going to flip it and multiply by 2. So when I flip it, it's gonna be 4 NO, 2 and 2 plus 2O2. And I'm going to change the sign and I'm going to multiply it by 2. So when you do that, you're going to have, it's going to be delta H, it's going to be negative then 180 times 2 Be 361A, so be negative 361. Okay, I think we're on the right track. Flip it and multiply it. Okay. Now, this, we ignore it. Now, look at ammonia. Ammonia, it's on my reactants, and on my reaction number 2 is on my product. So you want to flip it, and it looks like you're going to multiply it by 2 because you want 4 and you have 2. So you want to flip and then times 2. So it's going to be 4 ammonia, 2 and 2 plus 6H2. And since you flip it, it's going to be positive now. And it's going to be 183. 183.6 kilojoules. So now this equation doesn't exist anymore. Oxygen, I left it to the end because it appears in many places. So I just want to leave it alone. Now water, it's already in my products and it here is on my products, but I actually want 6, not 2. So I'm going to take this equation and multiply it by 3. So you're going to have 2 times 3, 6H2. In waters, you're going to have 3, plus. Plus 3O2 equals 6H2O. And you're going to multiply that times 3. So that's going to give you negative 1451.1 kilojoules. Now, add up your equations. And let's see if we end up. Notice that here we have 6H2 and 6H2 reactants and products cancel. Notice that we have, did I eat it all too? Mhm. We have to flip the first one. I don't think we have to flip the first one. And 2, no, we didn't have to flip this one. The first one didn't have to be flipped. So it's not gonna be this. We didn't have to flip it. We just had to multiply it by 2. And this is how we learn. So you don't flip it on this one. You just multiply it by 2. 2 and 2 plus 2O2, 4NO. There you go. So when you're adding them, you're gonna have 2 plus 3 O2s, you're gonna have 5 O2s. 2 and 2 and 2 and 2 cancel. So you're gonna have 4 NH3 plus, and then you have 4 NOs plus 6H2O. Now all you do is add up these numbers and you should have 906.3 kilojoules. We can do this one. I know I messed up a little bit, but We can do it together. And I'm gonna show you the answers. Where you're manipulating those equations. Manipulate them. And you end up with your final answer. And the answer should be exothermic because it has a negative value. Here's another question for you to practice on your own. Here's the answer. So we are going to switch topics and we are going to find one particular process of considering the formation. So it's going to call entropy of formation, which is the same idea, but it's delta. It's going to be delta F. Um, so we're going to be able to calculate entropy of formation, and basically is defined as the change of entropy whose reaction in which a compound is made from its constituent elements and their elemental form. Um, the one the one equation that I want to give to you that you only should become familiar with. Um, let me see. So there is going to be a table at the end of your textbook to give you the entropy of formation for each different if each different element. What I want you to recall though, that when we are dealing with the standard state in which the substance is most stable at 25 degrees Celsius in 1 atmosphere, that value of entropy, it's going to be um, it's going to be 0. So let me explain. Let me see if I can give you an example of that. Let me give you the equation that we are going to be using, and I want to explain what I meant where the standard state of any elemental element in their the heat of formation of any element in their standard state is 0. Why we care about the heat of formation, which is going to be a delta F. The reason why we are going to care is because we can use the heat of formation to calculate the entropy. This is another way of calculating the entropy of the overall reaction. So this is the sum of N, and then this is heat of formation of the products minus the sum of heat of formation of the reactants. Now, let's give you an example. Let's say I give you let me just get a new one. So let's say this is, I'm gonna write the reaction because we're gonna need the equation because we're gonna need it. So this is of the reaction equals the sum, M represents the coefficient, and we're gonna have the heat, the sum of the heat of formation of your products minus the sum of heat of formation of your reactants. Okay, you're gonna be given this equation. And let's say I give you this equation. Yes. Okay. You are going to have a table on your textbook with the heat of formation of each of these compounds. Pay attention to look at the states because they may be different values of ammonia for gas, solid, and liquid. So in your book, you're gonna have a heat of formation. So you're gonna have water, ammonia, and NO. You wanna make sure that water is in the liquid form, that ammonia is in the gas form, and that and nitrogen monoxide is on the gas form. And you're gonna have these values for delta H formation. It's gonna be kilojoules per mole. This is per mole. Okay, so the values you're gonna have in your textbook is gonna be negative 285.8, negative, let me see the numbers if I have it, negative 45.9, and this will be 91.3. Now, because I did not give you a series of other equations, you cannot use Hess's law in order to calculate the delta H over the overall reaction. So since you can't use Hess's law, you're going to use the heat of formation. And the way we're gonna do this is we are going to do the products. So let's do the products first. Notice that in the products, you have a 4, so you're gonna do 4 moles of NO times the heat of formation of NO, which is gonna be 91.3 kilojoules per 1 mole of NO. So remember, it's the sum. Plus, which another product do I have? I have water. So I'm gonna do 6 moles of water times, and water is gonna be negative 285 kilojoules per mole of water. And that number, when you do it in your calculator, it should give you, let's see, let's see what it gives you. So that should, and it's oh no, sorry. So that's gonna be 4NO times 91.3 kilojoules per mole. That's 6 times 285.8. That should give you 1349.6 kilojoules. So once again, I want to remind you that the reaction is 4NH3 gas plus 5 oxygens gas plus 4NO gas plus 6H2O liquid. Notice that we have your products and it's going to be, it should be a negative number. Okay, this should be a negative number. Now we want to go with the reactants. So to do the reactants, we're gonna have 4. Remember that the table for ammonia was NH3 was negative 45.9 kilojoules per mole. So it's going to be 4 because there's a 4 in front of ammonia, negative 45.9 kilojoules plus 5 oxygens. But notice for oxygen, I did not give you a number. The reason for that is because oxygen is in its standard state. What that means is that at 25 degrees, it's going to be gas. So because it's in the standard state, when an element is in the standard state, the heat of formation is going to be 0. So since we can put the 0, and that will give us, we do our math, and that should give us negative 183.6 kilojoules. Once again, I want to recall the reaction. So the equation is going to be delta H of the reaction equals the sum of your formation of products minus the sum of your formation of your reactants. Okay, so we have both numbers now. We have your formation of your products because so heat of the enthalpy of the reaction will be negative 1349.6 kilojoules minus negative 183.6 kilojoules. So the answer would be 1166 negative, sorry, kilojoules. And this is the delta H of this reaction. And the way we did that is by using heat of formation, of the reaction. So this is another method of finding delta H of the reaction. So you have different ways. You can either directly measure it, you can use by measuring Q, or you can use Hess's law, or you can use heat of formation in order to calculate the answer. So here's another method, which you can see that, notice here, this is the delta H of the reaction. So the 3 comes from there. This was given in the book. The 4 is from water. Notice here you have oxygen. It's 0 because if it's an element in their standard state, so it's going to be 0 for that. This is a table that you'll potentially be given for you to practice. This is another type of practice. This is bond enthalpy. Bond enthalpy is gonna be which bonds are broken and which bonds are formed. When we're dealing with a particular substance. So bond enthalpy is always positive because energy is required to break a chemical bond. Energy is always released when a chemical bond is formed between gaseous fragments. The greater the bond energy, the greater the bond, the strength of the bond. I don't know why it's doing it. So in order to calculate the delta H of a reaction equals the sum, this is another way of doing it, of the bonds broken minus the sum of the bonds formed. So with this one, it's a different table you're gonna be looking. So for example, you'll be looking at this. Notice here, this is bonds broken, and this is the reactants is bonds broken, and this is bonds formed. So for example, for doing this problem, notice that you're gonna have, you have H2 plus O2, and then it yields H2O2. So which ones are gonna be your bonds broken? Are gonna be this HH. So you're gonna look at HH and you're gonna see that it's 436. So you're gonna write, remember it's 436 plus, and then what is O double bond O? It's gonna be 498. 498. And that's going to give you, those are bonds broken. That's always gonna be a positive number. Now let's look at your bonds form. You have a HO bond and an HO bond. So you have two of those. So it's gonna be 2 times, where's the bond right there? It's gonna be 464 plus, and then you have an OO bond. An OO bond, which is gonna be 142. But remember, so when you do this number, you're gonna get 1070. But because it's the bonds form, that's gonna be a negative number. So when you do add this number plus the negative 470, you should have negative 136 kilojoules. So another way of doing it. So notice here's the steps. And then you have your final answer. Okay, here's another question for you to practice on your own. And here's the answer. We can definitely do some of these problems together. This concludes this chapter. I know it's a little rough at the end, but if you need more help, let me know.